All right. Hello, everybody. Welcome back to Comp 3430 Operating Systems. I hope that you're all having a good day today. We're getting real close to the end of the course. We've got I guess today and tomorrow, and then 4 more classes next week, and then we're done. So that feels like it's coming up pretty fast. It feels like it's coming up very fast. It feels like it's coming up very fast. I had a chance this morning to go and visit a high school, John Taylor, which is in St. James. My daughter was having a band concert or like a music concert that we heard about on Friday. The school told us on Friday that on Wednesday there's this concert that's happening. And it just happened to work out. And so I was able to go see that, and I don't know, I feel a little bit jealous because the kids that were there were like doing all sorts of cool stuff, like drumming on buckets and stuff and tap dancing, and they had like a dance where they were using parachutes and stuff. And all I really remember about elementary school music class was playing the recorder. That's it. Like that's all I remember being able to get to do in that class, and maybe xylophones and stuff. So I feel a little bit jealous of them. I hope that you're all doing okay today. What I want you to be able to do by the end of today's lecture is use condition variables in a program. So I want to keep working with this. I want to keep working with the threads example, the thread pool that we were taking a look at last class. And I want to fix it. The state that we were in last class was that it appeared as though threads were running, something was happening, but our threads did not actually finish all the work that was submitted to the pool before they started shutting down. Part of what I want to do with this today is I want to do a little bit more of a practical exercise of how do you use a debugger with multi-threaded code? How do you use LLDB to work with multi-threaded code? And how do you switch between threads of execution in the context of a debugger? The other thing that I want to get to time permitting today, because I think I might want to go a little bit off script, is I want us to start spending some time taking a look at some scheduling policies. So the ultimate goal here is that there's a bunch of different scheduling policies that are described in our textbook. So things like round robin, shortest job first, shortest time to completion first, and then ultimately this idea of this multi-level feedback queue. For each of these different policies, what I want us to be able to do is first evaluate the performance of the scheduling policies. And I want to evaluate the performance of these scheduling policies using a couple of different metrics. So there are 2 that are described in our textbook. There's response time and turnaround time. And these are calculated based on things like when the task arrives in the system, when it first gets to execute on the CPU, or when it first gets hold of the resource that we're managing with this scheduling policy. But I also want to kind of go off of what the textbook describes, and I want to spend some time thinking about the fairness of these scheduling policies. And I want to think about the fairness of these scheduling policies kind of in the context of like an infinite number of tasks that are coming in, as opposed to just the limited number of tasks that we might have in a system at any given time. Part of evaluating the performance of these scheduling policies then is going to be starting to compare and contrast these different scheduling policies. So based on for example, the response time, the performance of response time for a round robin, how does that change when we go to something like shortest time to completion first? Or how does that change when we go to something like the multi-level feedback queue, which is a little bit more involved than basic round robin? How are these different from each other? How are they the same? Are they fair? Are they not fair? I want us to be able to compare and contrast different scheduling policies. When we get to that, what I want to do is I want to mechanically apply scheduling policies. I want to go through the process of taking what's written down in our textbook and actually like, here's a worked example. Let's step through what's going on with these different tasks in the system. How is the system actually changing the state of the tasks? Where are the tasks right now as they're moving through the system? And then I want to record and measure the performance of the scheduling policies that we've got. So I have some printouts that I can share with you today, but I also have an electronic version of this document up on the webpage if you want to use an electronic version of this. But again, time permitting here, I don't want to overload what we're talking about today, because I felt like I did a pretty shitty job talking about assignment 3 yesterday, and so I want to spend some time actually talking about assignment 3 today. I want to spend some more time talking about that, kind of in relation to what we're doing today with condition variables and debugging our multi-threaded code. So I do want to start with just briefly taking a look at, or spending some time taking a look at using condition variables in a program again. So the state that we were in yesterday was we started to build this thread pool idea. So we're trying to take this design pattern and we're trying to apply this design pattern to threads. The design pattern that we're working with here is a resource pool. It's a resource management pool. And if you are thinking about the kinds of design patterns that this is a creational pattern. This is one that's used for when we're creating objects and getting instances of objects as their life kind of goes on. So I want to spend some time with the thread pool code that we had at the end of yesterday. I pushed that code up to this repository. So if you are following along with what we're doing on your own machine, please pull that repository today. And I'm going to pop over to my terminal and we're going to take a look at this code together. So the state that we were in at the end of yesterday was we were taking a look at 3430pool.c. In 3430pool.c, we've got our thread pool type here. We have a mutex and a condition variable that are in this thread pool object. The mutex here is used really for the entire pool. There are different parts of this pool that we're changing in different threads of execution. We've got a queue here of jobs. We've got an integer that represents the current number of threads that are still running in the system. We've got a flag that says whether or not this pool is shutting down right now. Shutting down the pool, this is something that's going to be effectively an atomic operation. I'm going to set this to false. This is one instruction to change this from true to false. I don't have to do anything different. It's loading a literal false into a memory location or a register. For these other ones, the number of threads that are currently running and the queue specifically here, these are non-trivial operations. These are non-atomic operations that we're going to be applying to these. When I reduce the number of threads that are currently running minus minus, this is not an atomic operation. This is at least 3 different instructions that we're working with here. And queuing something to a queue is many instructions. There's lots of stuff that's going on here. Dequeuing something from a queue, there are lots of instructions going on here. Even counting the number of nodes in this queue, there are a ton of instructions that are going on here, and none of these are atomic operations. So anytime any thread of execution wants to make changes to the queue in the thread pool, we're going to use that pool mutex to be able to do that. The work CV here, the condition variable, we're using this in the context of our threads, when they are initially created, start working in this worker thread function. And when they first start working in this worker thread function, they ask, are there any work tasks for me to do right now? If there are no tasks for them to do, they suspend themselves. They go to sleep, and the way that they're going to sleep is that they are waiting on this condition variable. The semantics of condition variables here are different slightly from locks. Where locks, we immediately enter this critical section. Condition variables are put yourself to sleep and in fact, release the lock, give up the lock while you are sleeping. This is a blocking operation, so the thread of execution that gets to this line will just get stuck here. It gets stuck here and it is waiting until I'm going to make this a little bit smaller. Is that still big enough for you at the back? Okay, awesome. It's waiting until the main thread of execution here begins to add tasks. So in this thread pool and queue function, this thread pool queue function, here is where our main thread of execution is submitting work. So if we have just 2 threads of execution here, one for the thread pool and one for the main thread of execution, the thread pool's thread is going to get stuck here waiting until the main thread of execution actually comes through and starts submitting tasks to the queue of jobs that we've got. it will signal to that one thread that's waiting or one of the threads that are waiting right now, hey, there's actually work for you to do right now. It will unlock this lock because it has been in the middle of making changes to the queue structure. And as soon as it has unlocked this lock, approximately, but in the context of timelines here, as soon as it has unlocked this lock, this other thread of execution will get the lock and it will wake up. So I'm going to quit this side. Once this thread wakes up, it's going to have the lock. It will be able to ask questions about this queue structure that we've got. Are there any jobs for me to do? Yes or no. If there are jobs for me to do, check again. Do I have jobs to do? DQ the job that I've got, unlock the lock because I hold the lock up until this point, and then actually start to do the work. Eventually, our main thread of execution is going to come back, and it's going to say, I'm all done submitting jobs. And when I'm all done submitting jobs here, this thread pool wait function is going to get called. I don't need to lock the pool when I do this. Again, this is an atomic operation. I'm setting a flag. I'm just changing the value from true to false here. This is just a store. There's no other operations that are happening here. And then while I still have threads running, I'm going to keep spinning around and telling them to wake up. Like, don't go to sleep on this condition variable, or if you are currently sleeping on this condition variable, wake up. Recognize that this flag has been set so that you start shutting yourself down. Yeah.
So now I've got a question.
Yes, please.
Everything signal, why don't we just broadcast? And on the other end, why would threads go to sleep once they have been awoken and there aren't any amount of threads still, or if any jobs still left? Like, I don't know. It feels weird to keep moving here.
So this, I believe, is what you're suggesting, yeah? Yeah. So if we did it this way, lock, acquire the lock, send it to everyone that's currently waiting, and this is a fair point. Everyone that's currently waiting is going to be blocked currently right here. Anyone that's not waiting will either be inside of this part, so between line 43 and 57, not waiting, but they hold the lock, so we wouldn't be able to send a signal. But that means that if they're exiting this region here, they've been able to succeed in getting a task. By the time they get back up to the top here, the flag should be set, and we should stop. Yeah, so broadcasting instead of spinning here is a fair suggestion. And I will take that suggestion and I will apply it to this code. Yeah, okay, all right. Good question. Are there any other questions about this code? Yeah.
If a job is triggered, the thread will lock the whole pool, and you can't, I guess, update the boolean flags anymore until you let that go.
We'll be able to, so the question is, should we have a lock just for the queue structure, right? Is that the question? Yeah. Should we have a lock just for the queue structure? That would be a fair addition to this. So instead of having a pool mutex that locks the entire pool, we could have things like pthread mutex t jobs mutex here. I could have this, and that's only going to be when I'm trying to read or manipulate the queue structure that this would be used. I'm doing it the way that I've done it with just one lock for simplicity's sake, just to try and keep this example that is already quite big, smaller than it might otherwise be. But this would also be a reasonable suggestion so that you could do things like make changes to the number of threads here while I'm adding something to the queue if I wanted to. I'll come to you in just a second, but another thing that I'm going to point out here, I'm going to delete that line and I'm going to save this. All of this is ultimately inspired by this document here. This is a publicly available thread pool example that is published in some Oracle documentation. Oh my God, no, I don't want to accept any of these cookies. This is an example of a thread pool that does things like having many condition variables here as opposed to just one condition variable. And having many condition variables here is too many. It's too many. I want to have just one. I just want to have one. So if you want to see a more complete and complex example of a thread pool, you should take a look at the README here. But yeah, I don't want to spend any time looking at this. In the past, when I do this example, I would basically start by looking at that. And that was too much. That was just way too much. So instead, we're just gonna we're kind of working on this smaller example from the beginning. Yeah.
DB for the queue, you could just implement inside of the queue, right? Like at this level, you wouldn't need to be aware of any DB inside of the itself, right?
So I suppose. So in 3430 pool, I've got this job queue.c. I could have the condition variable here, I guess, and then I could have multiple different queues of tasks that have different priorities. And now we're starting to think about scheduling more than just basic things. But we could move that condition variable to this structure, sure. If this is ultimately hidden inside of our implementation of the pool, that would be a fair thing to do. But I may also want to use this queue somewhere else. I might not have just a job queue. I might have a general queue. And at that point, I don't want to put condition variables for jobs in a queue that's just a queue structure as opposed to specifically for this purpose. Yeah.
In pool, for the while loop, should there be a check for the inside or
So this part right here, yeah, this is where we're going to get to today, ultimately, yes. So don't spoil it for everybody else. But yes, yeah, that's effectively where we're going to get to today. Yeah. All right, so a couple of the things that I want to do here are, we are in a state where our code compiles, but now we have multi-threaded code as opposed to just single-threaded code. And what I really want to do with this is I want to start understanding why my code doesn't actually appear to do what I am expecting it to do. So pool adder here is using our thread pool, but now we're getting into states like this, where I'm not actually getting anything at this point showing up in the output of the tasks that I'm submitting to the thread pool. So I'm going to run LLDB on this. And the first thing I'm going to do is I'm going to set a breakpoint at the main function in the pool adder function. I'm going to start this up, and I'm going to start stepping through this. I want to step through thread pool create. And what I want to do stepping through thread pool create is I want to start by listing the threads that are currently running in this process. So within LLDB, and I'm not sure what the instructions for this would be for GDB if you're using GDB instead of LLDB, but it should be similar between the two of them. To list the current set of threads that are running in this process, we use the command thread list. This is going to show us that currently there is one thread of execution in this program, and the thread of execution is the main thread of execution that got started when this process was created. I'm going to step through a couple of lines here in the creation part, and I'm going to get to the point of starting to call pthread create. So on line 97 here is where we're going to initially start adding these threads of execution to the process that we've got. And when I do thread list now, there's two. There are two threads of execution that are running in this process right now. I'm going to finish stepping through this loop. And now, when I do thread list, I've created two additional threads of execution. So I've got thread number 1, thread number 2, and thread number 3. Thread number 1, this is the main thread of execution that I'm currently looking at, and the asterisk here is saying that that's where you are. This is the thread that you're currently looking at right now. I want to see what my other threads of execution are doing. They are blocked right now. They're not doing anything, or they don't appear to be doing anything. And so to take a look at the state of another thread of execution, I can do thread select, and then I can pass to it the thread number that I want to choose. So I'm going to select thread number 3. Thread number 3 is somewhere in some code that I don't currently control. It's in a file that has a suffix .uppercase-s. This is assembly language code that has been used in the compilation of my program, and it is something about system calls. I don't really know what this is or where we are, but what I do know is that I can go up in frames. So I can go up the stack of the calls that have been currently made by this thread of execution. And I'm going to keep going up until I get out of libc.so. And once I keep going up here, I do eventually get back into my own code. And what I can see here is that this thread of execution is currently stuck. It's blocked on this condition variable. It's waiting for this thing to happen. So I'm going to put a breakpoint at line 52 here. And what I want is, I want this thread of execution, or the thread of execution that wakes up when there's a task submitted to this, to breakpoint here. I want to stop so that I can start inspecting this stuff. So I'm going to do thread select 1. I'm going to go back to thread number 1 here, and then I'm going to continue stepping through the main thread of execution. Threads 2 and 3 are both blocked right now on that function to wait for the signal to be sent to us. So in the main thread of execution, we've just finished making our thread pool, and we're just about to start submitting work to our thread pool. And so what I want to do here is step through this job creation part. We're going to acquire this lock. I'm going to print out the value here, pool mutex. Pool mutex here will tell us all sorts of stuff, but it will also say things like what the owner of this lock is, which if we do thread list, I believe is the thread ID that we've got here. This is the thread ID that we've got, and this is the owner of the lock, so we can see which thread ID currently holds the lock that we're looking at. The state that I'm in right now is I'm going to start sending the signal to this thread of execution. It's not immediately going to wake up because it cannot hold the lock. I hold the lock right now. This thread of execution that I'm stepping through right now is what holds the lock, so that other thread of execution cannot wake up. But sometime after unlocking this lock, I guess immediately after I hit N here, that other thread is actually able to take over, and it's actually able to hold the lock now. So I've hit this breakpoint now of I'm asking the question about the size of the queue that I've got here. If I step through this, I'm going to see that I am able to get to the point of stepping over some stuff and then go back to my main thread of execution. This one is now stuck spinning in this loop indefinitely. And I'll finish submitting these jobs. There are 1,000 of them, so I'll break on line 38 here and continue. And then I'm going to go into thread pool wait. I'm going to set that flag, and I want to check out what my other threads are doing right now. So thread select 1, thread select 2. It's still stuck in this loop. Thread select 3. It's also stuck in this loop. They're both happily spinning away, doing the work that I asked them to do. I'm going to go back to thread 1. I'm going to hit continue here. And they're both going to exit. And the problem that I believe that we're seeing, and I'm going to set a breakpoint here on this line, which is the question we were asking about, should we be checking the size of the queue? So this is line 30 here. I'm going to set a breakpoint on line 30. And I'm going to restart this program. I'm going to hit continue here. And we've hit a breakpoint on thread number 2. So this is not our main thread of execution anymore. Our main thread of execution never actually gets to this point because it's one of the worker threads that we're launching. The state of our pool right now is pool underscore wait. It is false. So if I continue to step through this, we finish. I set a breakpoint on line 30. It's never getting to that point. I'm just going to quit, and we're just going to fix the problem. So let's take a look at pool adder. Let's take a look at 3430 pool.c. Quit. I'm already editing it right now. OK. Here's what I want to do. I want to change this just a little bit. I want to change this to be, I don't want to shut down if the pool wait flag has been set. I don't want to blindly just stop accepting jobs. But in this case, I'm also not just going to ask questions about the state of the thread pool itself. I'm going to add another flag here, but the flag that I'm going to be adding is going to be a thread local thing. So I'm going to say Boolean, bool shutting down is equal to false. Thread local flag indicating whether or not we should stop running jobs when the jobs run out. We should stop waiting for jobs. So this is going to be a flag that every thread of execution is going to have for themselves. And we're going to set this flag only when we have this thread pool wait flag set, and also we're in a state of there's no tasks left in the pool. This effectively will turn into queue size is equal to 0 and the pool wait flag has been set. But I'm kind of breaking this into its own flag for myself just to help keep myself kind of where I want to be here. So I'm going to change this to be while pool does not equal null and while not shutting down. The other place that I'm going to make a change here please forgive me, I just want to check to see that we are still actually streaming this. It looks like it. Okay, I think we're okay. The other place I want to make a change here is going to be closer to the bottom of the implementation of this. So one of the questions that I left you with yesterday is, there are conditions that we can have in this code right now where we can exit this loop without ever unlocking the lock. The conditions that we can exit the loop are the state where we are waiting for this signal to be sent to us. We receive the signal, but the queue size is equal to 0. If the queue size is equal to 0, then I'm never going to unlock the lock. I will never unlock the lock. So the way that I want to change this is I'm going to have an else part of this, else. The else part of this is going to ask 2 questions. It's going to ask 1 question. The first question is the queue size are there no jobs left? And are we shutting down? If that's the case, then I'm going to say shutting down is equal to true. And the situation that we're in right now is that there are no jobs left in the queue, and the flag has been set to say that no more jobs are going to be submitted. So our main thread has said shut down. I'm waiting for you to finish. I'm blocked, so I'm not doing anything right now, but I want to make sure that you actually finish all the tasks that you're supposed to finish. But now there are none left, and so I want you to start shutting down. If there are jobs left in the queue, then I still want to keep doing them, but I'm gonna need to unlock the lock. So if there's no jobs left in the queue, sorry, but we're not in the state of shutting down, I might just get more jobs later. I still need to unlock this lock. So I'm gonna say pthread mutex unlock. Unlock the lock. I want to make sure that other threads of execution are going to be able to enter that loop. I want to make sure that other threads of execution, like the main thread of execution, will be able to submit more work to me at some point. I'm going to write this out. I'm going to zoom out. I'm going to make this. And I'm going to run pool adder. And I'm going to just desperately hope that this works. And I'm going to change this code. I'm actually going to go back down to thread pool wait. Okay. We changed this to conn broadcast, and I still think that was a good idea. And I'm not going to throw you under the bus and say that you broke my code, because I'm the one that just did it. I said, hey, that's a great idea, and then I did it. Here's the problem. With thread pool wait, conn broadcast will broadcast, and then it will immediately finish. But I want my wait to block while there are still threads running. So I'm going to uncomment this loop. I'm going to throw myself under the bus here. I made this change. I want this to loop because I want to wait while there are threads still running. If there are threads still running, they're still doing work. If my main thread of execution here gets to thread pool wait, and it then gets to return because it's not waiting around for those children to finish, this is that state where we're getting into making the exit system call effectively, and we're just forcing those other threads of execution to shut down at that point. So I'm going to write this out, I'm going to make it, and I'm going to run it one more time. Okay, good. And now we just seem to be stuck. I'm going to hit Control C on my keyboard. I'm going to run this in LLDB one more time. This time I'm just going to run. I'm not going to set breakpoints. I'm not going to try to stop on anything. I'm just going to start this thing running. And then I'm going to hit Control C. And I'm going to zoom into my debugger here. I'm going to do thread list. We have 3 threads of execution that are running. They are all working right now. So that's actually good. That means they're making progress. I'm going to hit C to continue. I'm going to let this run for a little while longer. I'm going to hit Control C on my keyboard. I'm going to do thread list. They're all working. Honestly, I think this is actually okay. I'm going to hit Control D on my keyboard to get out of my debugger. And I'm going to edit pooladder.c. And I'm going to change this to 10 jobs instead of 1,000. Okay. The jobs were just taking too long. The jobs are just taking too long. The jobs were taking too long. Good, that's a good problem to have. Oh my gosh, okay, thread pools. We're all on the same page. We're all on the same page. Let's start talking about fucking thread pools. Okay. Why though? I mean, I've dwelled on this for long enough. I've spent enough time on this, but why? Why are we doing this? What is the purpose of this pattern that we're working with right now? One is that we could have lots and lots of short-lived tasks. So the tasks that I'm submitting here with this pool adder, they are long-running tasks. These are not really trivial tasks. I'm counting up to 200 million or whatever. While this isn't actually accomplishing very much, this is non-trivial work and it takes quite a lot of time to do. If I have a lot of short-lived tasks that are adding 1 to a number, it's going to take way more time to create a thread to do that than it is to just do the work that I've asked to do. So the time to launch a thread takes a lot longer than it does to actually run the task itself. That cost adds up and up and up and up. If we can just make a bunch at the beginning and then reuse them over and over and over again, the initial cost of creation goes down. So this is that amortization idea that I gave you when we first started to justify this, this design pattern. The other reason is if we have n tasks and n is much, much, much bigger than the available number of CPU cores that we have, starting n threads that is much, much, much bigger than the available CPU cores that we have will lead to lots and lots and lots of context switching. If I make 50,000 threads of execution, we're going to have to switch through 50,000 threads of execution so that they all get a turn on the processor. Context switching is not free. Context switching involves that whole path that we were thinking about with processes. We have to do a mode switch. We have this hardware timer interrupt. The operating system has to take the current state of the CPU and save it into the context of this task, the task struct in Linux's case. We have to pull another one out and put it on the processor. We have to do the mode switch into that code so that it can actually start running again. And then we just have to keep doing this over and over and over again. And so then context switching becomes the massive overhead that we have between all of these threads of execution, and they don't get to finish the work that they're supposed to finish. This idea is thrashing. This is where we have multiple tasks that are taking so much time to switch between each of them that we never actually get any work done. And so what I want to show you really quickly here is when I do make this back to 1,000 total jobs here that are being executed by 2 different threads, if I run pool adder here, I'm going to open up a new terminal and I'm going to run top. And what we're going to see here is that pool adder right now is taking 300% CPU. And that means that it's effectively taking up 3 CPUs in my system. I've got 16 in total and it's using 3 of those. 2 of them are counting up to 200 million over and over and over again. One of them is just constantly spinning and sending signals to the other threads to say, hey, wake up, there's no more tasks for you to do. I'm blocked in this main thread of execution. But this is never going to use more than 2 CPU cores to count up to 200 million. No matter how many tasks I submit to this, it will always only use 2 CPU cores. And that effectively means that the thread that gets on that core just gets to keep the core for a long time. If we look up here, I've got 32% of my CPU being used. So again, spread across 16 different CPUs. That one task is just going to get to stay on that CPU for a long time because there's lots of other CPUs that are available for other tasks to work on. Now it's done. So if I go back here, we can see that we get some giant output here that's 1,000 times more than the 200 million that we were working with in the first place. So the idea with thread pools here is that if we have lots and lots of tasks that take less time than it takes to launch a thread, then we can use this design pattern to help us amortize the cost of creating the threads in the first place. If we have lots of long-running tasks that we don't want to have thrashing between different CPUs, using this design pattern will help us limit the number of concurrently running processes at any given time, even if we have lots and lots of tasks that we eventually need to be able to finish. When I was working in industry, this is the reason why I was using this design pattern. I would have lots of tasks that I need to do, but I know that I only have 10 cores on this system, and I never want to have more than 10 things running at the same time. So limit the number of concurrently running things to 10 using something like a thread pool like this. All right, are there any questions about this before we leave thread pools behind us? Yes, your hand was up first, so yeah. Awesome. Yeah. I will stop streaming. Am I streaming now? Does it take a... Oh, okay. I'm hoping you can hear me now. I'm hoping you can hear me now. If I missed lots of this, I'll make a video after class shouting at my computer about why it shouldn't stop suddenly. It's not switching back to the presentation slides. I'm going to exit OBS and then come back. So again, forgive me if you're on the stream right now, please. I think it's, oh my God, I think it's streaming. Okay, awesome. We are streaming right now. I mean, I've been just shouting up about these 2 points for the last little bit. So if you are watching this video after the class, these are the 2 points that I've been talking about. This is where I want to go off script. This is where we will eventually get to thinking about scheduling. But I do want to take a look at assignment 3. I want to give it the right amount of time as opposed to just the last 5 minutes of the class. And I look at the time here to make sure that it's not actually the last 5 minutes of class. I feel like I did a bad job of this yesterday, and so I want to come back to this. I don't want to dwell too much on the purpose of the assignment. The purpose of the assignment, as I discussed yesterday, is multi-threading. The goal here is that I want you to implement your own multi-threading library. There are different parts to the multi-threading library that I'm looking for you to implement, and a lot of the stuff that's the initial setup for this assignment you can get started with at any point now. You should be able to get started with a lot of this stuff. I'm going to recommend that when you're working with implementing this concurrency stuff, that you start with implementing locks, then move on to implementing threads themselves, and then after that, move on to implementing the scheduling policies. The lock implementation that I'm looking for you to implement is something that looks a lot like what pthread mutex lock looks like. The interface that I'm looking for you to implement is the one that's in nqpthreadlocks.h. And so that's this file right here. And there are 4 functions that I'm looking for you to implement. One is to initialize the lock structure that you are implementing yourself internally. Then there's lock and unlock operations. And finally, there's a destroy, so a destructor function here. The locks that I'm looking for you to implement are just spin locks. I'm not looking for any of the more complicated locking mechanisms, so this is something that will just do the basic spin lock implementation using the atomic instructions for test and set. So using this test and set idea and an atomic flag, I want you to be able to implement a spin lock for this. The atomic stuff is something that you can get from this header right here. STD atomic is part of the C standard library, and it has a few different things that you can use. One of them here is an atomic flag type. This is what the flag is going to be in your lock implementation for the value. So you shouldn't just use basic integers here. You should use one of these atomic flags. And the reason that you must use one of these atomic flags is that you're going to be calling this function here, atomic flag test and set. This is going to be what invokes that assembly language instruction on x86 that is compare and exchange. So like actually do this all in one operation. Like, give me the value of what it is right now and then swap it with something else if necessary. Test this value that I have right now, check to see if it is the value that I'm expecting, and if it's not the value that I'm expecting, or if it is the value that I'm expecting, set it as one single atomic operation. For implementing your own locks here, it kind of has to be atomic. It has to be atomic because what I want you to do with your implementation of locks here is I want you to evaluate your implementation of locks for correctness. The way that I want you to evaluate your implementation of locks for correctness, so like actually enforcing mutual exclusion here, is I want you to provide some sample code that uses the lock that you've implemented here with pthreads. You are more than welcome to take any of the samples that we have done in class and modify them to use your lock implementation, but with pthreads. So the textbook sample, for example, the one where we have this messed up number because we're losing add operations, you are more than welcome to use that, but I want you to use this implementation of locks with actual pthreads. That's something that you should submit as part of your assignment. Eventually, when you get to implementing threads and when you get to implementing scheduling policies, your spin locks shouldn't just spin. Eventually, when you get to implementing scheduling policies, you're going to have to change your code a little bit so that the spinning part will yield as opposed to just blindly spinning, because we don't have preemption in the threading and concurrency that we're going to be implementing here. The code that you implement in the end should actually work for both cases. It should work with pthreads and it should work with NQP threads. It should work for both of them interchangeably, and it shouldn't have to be modified to do that. Internally, you'll have to keep a little bit of state when you get to the point of implementing this yield function, and I'll talk about that in a moment. You'll just have to keep track of a little bit of state that says, I've initialized some thread or I haven't initialized some thread. If you haven't initialized threads yourself, then you're probably using pthreads and real concurrency, so the yield will just do nothing. If you are using NQP threads, then the yield should yield as appropriate. With threads, what we're going to be doing is kind of building up our own primitives here for our thread types. So I'm looking for you to implement a couple parts to this. The first part here is going to be to build a thread control block. I want you to build your own kind of process control block or thread control block or task structure effectively. The task structure that we saw in the Linux kernel is hundreds and hundreds of lines long. We don't need to do that. We do not need to do that. Instead, we're actually going to have a pretty limited thread control block. You may add more stuff as you start building this up, but minimally, you need to have two things in your thread control block. The first is a context. And the context is literally the state of the CPU as your task is being taken off of the CPU or as it's being put onto the CPU. The other thing that you're going to need to have is a stack. You're going to have a stack for this thread of execution. Every thread of execution is going to have its own stack. The first interface that I'm looking for you to implement for this is, NQP thread.h. There are two functions here in NQP thread.h. One of them is the create function, and this is effectively the same in terms of like what it accomplishes as pthread create. So this will make a new thread of execution, and you will be given a function pointer and then arguments to that function pointer. The signature that you have here is effectively the same as what the pthread create functions are expecting. NQP thread join is a blocking function that should wait for this past thread of execution to finish. If it's still running, it should block. If it's not running, it should just return immediately. When that task is finished, it should return. It should be able to return back to whoever is calling this code. The thread control blocks themselves So the type that we have up here, which is NQP thread T, this is effectively what you will be building inside of your implementation. The thread control blocks themselves have to have a context and they have to have a stack. I'm really grateful that there are libraries for us to use for contexts. We don't have to write assembly language instructions to be able to get the state of our CPU. Instead, what we can do is call this function getContext on Linux systems. And what getContext returns to us is an instance of this uContextT type. We don't actually need to know anything about this. You can take a look at it in your debugger if you want to, but you're never actually going to modify this structure state internally in your own code. But what you can know is that this is the machine state. If you start looking at this in your debugger, you're going to start to see register values for the CPU as it is right now. So you'll see the set of the generic registers, and then you'll see floating point registers, and you're going to see all sorts of cool stuff. But you don't need to know about it. You don't need to modify it. You can just assume that this library will provide that for us, which is great because I don't want to write that assembly language instruction stuff. You're going to have to include this uContextT.h to be able to get a context in the first place, but each of the threads of execution in your code will have to have an instance of a thread context here so that they can start to operate. The other thing that you're going to need to do here is to start taking the context that is returned. And I'm going to pop back to the terminal, to the manual page here. What the getContext function does is it returns the state of the CPU upon entering this function. So that means that the stack pointer is going to be whatever it was before you entered getContext. The current program counter is going to be effectively leaving the getContext function. So you're returning from this state. And that's cool, but it's not useful in terms of being able to like switch between things in a meaningful way. So to be able to switch between things in a meaningful way, we have to then start to work with this function that's called makeContext. MakeContext takes an instance of the context. This is a terrible name for a function because it doesn't actually create a new context, but rather it manipulates an existing context. This takes 3 arguments. The context that you want to manipulate, so this is the machine state that you got from getContext right here. It takes a function pointer here. This is the function pointer that will have been passed to NQP thread create. So this is the function that you want to be at the bottom of the stack for this context. It takes an integer that represents the number of arguments that this function will take, and then this ... here is, these are the arguments that you'd actually pass to that. Conveniently for us, the function that we accept in NQP thread create is a function that takes exactly 1 argument, and it is a void pointer. So when we're working with makeContext here, we can actually hard code a 1 here because we will only ever accept 1 argument to this function. It will be that void pointer type that we have accepted as the argument to this to the create function. What you pass here is effectively going to be that arg value, so you can just kind of blindly pass that through to this. What makeContext does here is it will take this context that you got from makeContext. It will make the stack have this frame in it and this frame in it only. And it will pass to that function when it begins to run the arguments that you pass to it, which are going to be that void pointer argument that you pass to the create function. The other thing that you want to do with the context once you get it back, I'm going to scroll down here a little bit. I'm going to scroll down to makeContext here. I like this manual page from makeContext because it then includes a good example of using this function, not for the purpose that we're using it for, but it shows like how you could use it to accomplish something that looks like what we're starting to work with here. So in the main function of this example, at the bottom of the manual page for swap context, we're doing a few different things. The first is that we're making two stacks. These are two arrays. They're just two buffers. They're two character arrays. They're stack allocated for the main thread of execution here. But you can also dynamically allocate this. You can call malloc if you want to, but eventually you're going to have to set the stack for this thing. Then we call getContext here. And once we return from getContext, we are manipulating the context that was passed to us to set the stack itself. SSSP here, SP is stack pointer. And so I'm passing to it the array that represents the stack for this thread of execution. Size here represents the number of bytes that are in that stack. I'm going to recommend that for the size of the stack that you use this constant from signal.h as opposed to just blindly using this made up number that's in the example here. But you can set the size of the stack to be that. When I'm implementing this, and I'm going to say that when you're implementing this, you probably don't need to use this property. The link function says when this context returns from the function that's on its stack, the last function that's on its stack, go to this part. Go back to the main function here. And I don't really want to do that. I don't want to do that because what we're eventually going to do is we're just going to be doing the thread management ourselves. We're going to be swapping between things ourselves as opposed to allowing it to return to something. The last part here is calling makeContext. So after we've set the stack and its size, we're going to pass the context itself, the function that we want it to run, and then the arguments. This function here, func1 up at the top, takes no arguments. But again, when we're calling makeContext, we're going to hard code 1 and we're going to pass arg to this, or the arguments that have been passed to us in NQP thread create. The next part here is making another context. So it's doing the same thing here. It's setting the stack pointer and it's setting the size. This is doing some magic with this link property. Again, I didn't actually use this in my own implementation. You might find a reason to want to use this, but I didn't use this anywhere in my code. We call this makeContext. And then eventually what we do is we swap contexts. Swapping context here takes two arguments. The first argument, this one here, this is the context that we are swapping from. What happens is the current state of our CPU is going to be put into this context. So on this line right here, the program counter, the stack pointer, all that stuff is going to be put into UTX main here. And the second argument is going to be the context that we want to start executing. This function effectively does not return in the same way that exec does not really return. What we're asking to have happen here is I want to take the context that's on the CPU right now and take it off, save it into the context that's the first argument, and I want to take the second argument, that context, and put it on the CPU. And so we are effectively changing the program counter and we're just going to be somewhere else in our code. Yeah. It will be like it's returning from swap context. In this case here, yes, yeah. So if I were to swap back to this context, this is what the question is. If I put this as the second argument of swap context, then we would come back to effectively returning from this function here. In this code, the order of operations here is that once we get to this line, this swap context, when we swap to the context that is uContext func2, we are now going to start executing here. In your debugger, because we're definitely going to be using debuggers with this assignment, when you're in your debugger, I don't know, I say that about myself. I'm sorry, I used a debugger a lot in this assignment. In your debugger, if you do next on swap context here, you just kind of like, you wind up in assembly language code and then you never actually get to where you want to go. In your debugger, what I would suggest is that you set a breakpoint on this line. So if you know that you're going to go to this place in the code, set the breakpoint on that line and then hit C to continue, then allow swap context to finish, and then the breakpoint will get fired and you'll get stuck at that point. When we do thread list here, there will be one thread because we're only doing this in one thread of execution. We're managing the rest of the thread stuff ourselves here. So the context here, the order of operations here is that when we swap to this context, we're going to start running in this function. We print this, and then we do swap context again here. Swap context is going to save the state of what we were in function 2 and put the function 1 context onto the CPU. So change the program counter, change the stack. Then we're going to start running up here, and we're going to print out these things. We're going to do the swap context again. We're going to save the state of where we're in right now, and we're going to switch back to function 2's context at that point. That means that we are effectively returning from this function. We'll print out this, and then we end this function. In the sample code that they have here, the setup is that this UTX func2 context has a link to the func1 context, and so it effectively returns to that point. But in our case, what we're going to have is our threads of execution are calling functions in our library so that we will be able to swap context ourselves as opposed to just allowing them to switch to another one kind of magically with this link property. So in this example, what happens is returning from func2 will cause us to go back to this point where we're effectively returning from swap context here. We will print out returning from func1, and that will have the effect of going back to the main function here, which is where we'll be returning effectively from this point here, printing out exiting from the main function and then exiting from this process. Make context and swap context are what we're going to be using. The other function that you might be using in your implementation is set context. Set context here, it's in this manual page, sorry. Set context here takes one argument. And unlike swap context, it doesn't save the current state. It just switches to that context immediately. So it doesn't save where we are right now. It just switches to the context that you have passed to it. So in your code, you will definitely be using get context. You may use set context in some circumstances. Most of the time, you're going to be using swap context, and make context will be used in conjunction with get context. In the library that you're implementing here, NQP thread create will call get context. This is where you're initially going to get a context. This is where you're going to call make context. This is where you're going to change the stack and initialize the stack so that it has one stack frame in it, so that when you do eventually schedule this task or swap to this context, you'll be able to get to the function that's being passed here. That's the thread creation stuff. Once you've got your thread creation stuff working, then you're going to want to start switching between tasks. The initial approach to this, and what I would suggest that you do, is to have just 2 tasks running. So I'm going to go back to my terminal here, and I'm going to open up nqp printer.c. nqp printer.c, this is the one that we were looking at and running yesterday that kind of just finished immediately. I'm going to comment this line out, but I'm going to create 2 threads of execution here. Printer is the name of the function that's just above this one, and all it does is print a letter and then print a number after it. The argument that I'm passing here is I want one to print A and I want one to print B. I want them to switch back and forth here. NQP schedule start is the next function that I'd suggest that you start looking at after you've created these 2 things. NQP schedule start is described in this header right here. And NQP Schedule Start says, I've finished creating threads of execution. I want you to start scheduling these threads of execution. Your initial implementation of this should be the default scheduling policy, which is just switch back and forth between two threads of execution. So there's no complex mechanism for determining which one gets to go next. It's always just the other one gets to go next. Switch back and forth between the two of them. NQP Schedule Start is going to start taking tasks that are in the system and then causing them to be scheduled. This is the function where you're going to actually start calling swap context. This is the function where you're actually going to start calling set context. This is where you're going to start actually taking these contexts and putting them on the CPU. So this is where the scheduling will start to happen here. Eventually, what will happen with these samples that I've given you is that once you swap to this context, so let's say we're starting with thread A here, once you swap to this context, you're going to start running in this printer function. Just like we are with NQP, with pthreads. You're going to start executing code inside the function that you're passing to this. All the examples that I have given you in the repository for this assignment will always call two functions. One is they will call NQP yield. This is a cooperative multitasking system. NQP yield is your opportunity to switch to a different task. This is code that you will be writing that will eventually say, take the task that's running right now and swap off of that and swap to another task. The other function that they will eventually call is NQP exit. NQP exit says, this thread of execution is done. It's not going to do anything else. You should never schedule it again. You should remove it from your system if you have some representation of this in your system. I'm going to take a look now at NQP sketch.c. NQP thread.c, I'm sorry. NQP thread.c is where I would expect you to put your implementations for both NQP thread.h and NQP thread sketch.h. NQP thread create eventually should accept n tasks that we want to start and put them into a queue. Eventually put them into a queue structure for your scheduling policies. NQP thread sketch has the functions that we're using here to do things like scheduling tasks, switching to other tasks, or removing the task from the system that we've got. Both of these need to know about this queue structure that you're going to have internally. For the initial part, again, what I would suggest that you do is just kind of set it up so that there's just two tasks. You can just hard code these as two tasks rather than building a queue structure if you want, and then just switch back and forth between them every time NQP yield is called until they both call NQP exit, and then there's nothing left for them to do. I'm going to go down here to scheduling. We haven't talked about scheduling yet in this class. We're going to talk about it immediately after we finish this, so tomorrow at this point. But there are three policies that I want you to implement. They are straightforward policies. First in, first out is not preemptive at all. And so when I say not preemptive, what I mean in our context is calling yield will do nothing. Tasks will finish before they give up control of the processor. The tasks are going to call yield, but you should just ignore what they're telling you. Don't let them give up control of the processor. Round robin is a queue structure, and you're going to take a task off and put it back on the end, and then kind of work through them this way as they are calling yield. The multi-level feedback queue, we'll spend a little bit of time talking about this tomorrow, but I'll give you some advice right now, which is that all of my implementations of these different policies use exactly one queue. I don't have multiple queues. Multi-level feedback queue, as it's described in our textbook, is a list of queue structures. I didn't implement this as a list of queue structures. I implemented this as a simple priority queue as opposed to a list of queue structures. And that just saved me a lot of time of having to keep track of where all the different tasks are at any given time. And it simplified things like having to take tasks out of one queue and put them into a different queue. If they're always in the same queue, then I will only need to have to worry about that one. I'm going to go down here to the assessment part. The lock implementation here, again, with this idea of locks, I'm looking for you to implement locks in such a way that eventually they work with both pthreads, which is code that you are going to have to supply in your submission. So when you hand something in, there's going to have to be an additional file that you're either pulling from class samples and modifying to use NQP locks instead of pthread locks. They're also going to have to work for the NQP samples that I've given to you. The assessment of threads here is going to be initially that we're going to have two threads that are working back and forth. In terms of reading these assessments for this assignment, I'm going to suggest that you kind of like start at the bottom and work your way upwards. The way that I implemented this is effectively what I've encoded into this. So I started my implementation by working with just switch two back and forth between each other. Switch two back and forth between each other, and they don't have continuous state. Every time it would just start at 0 and then start at 0 and then start at 0 and then start at 0. And then eventually I got to the point of being able to have them keep state. So start at 0, but then next time start at 50, and then next time start at 100, that sort of thing. Eventually what you're going to get to is that you are going to have more than two threads of execution that are running. They appear to run concurrently. Again, in this case, it's at the same time. They're not literally at the same time. We're just switching back and forth between them so fast that it appears that they are all running at the same time. And then the main thread of execution, which is the one that's calling functions in all of the samples. So our main function, it will eventually get control back. To be assessed is that all of the sample code that I've given you here in the repository. So I'm going to take a look at NQP Refiner here. All of these examples at the end, the main function will print all done. And so the way that I'm going to ask the graders to assess that you have given control back to the main function after everything is finished is that the words all done appear at the bottom. The main thread will get control back and it will finish. Yeah. Can you put it in any other function? Can you just print out? Yeah. No, sorry. These samples, I'm going to ask effectively that you don't modify these except in one context. You're welcome to change them, like if you want to change the policy to see how it affects the way that your code is working, please do that. But ultimately, the graders are going to be using these code samples, so adding all done somewhere else is going to change the way that that's working in the end. I will also suggest that if you do print anything in your implementation of scheduling and threads, that you print a standard error instead of printing to standard output. So all of these examples are going to print a standard output in some way, shape, or form. If you are printing anything to standard error, I'm going to suggest that you tell the graders in your README, like redirect standard error to this file so that you can just see the regular output of what's supposed to happen with this thing. The scheduling policies themselves are going to be assessed independently. So each of them are going to be assessed based on approximately what they look like in terms of their output. And I want to emphasize with MLFQ that when we're assessing MLFQ, and we'll talk about MLFQ tomorrow, but when we're assessing MLFQ, the general idea is that what I'm interested in seeing is MLFQ-like properties of your output. Round robin, I've got no minutes left here, but NQPprinter.c by default will use round robin. I'm going to do this one here. NQP sketch tasks is something that will just print out letters here. I'm going to comment out this line, and I'm going to say here that round robin NQP sketch tasks will just kind of switch back and forth between each of these different tasks every time that they call yield. So the output here is that we've got ISN, ISN, ISN over and over and over again. MLFQ and MLFQ-like properties here. When I say that is, we'll talk more about this tomorrow. Again, print a standard error. MLFQ-like properties is that eventually we get into the state where these things that are interactive tasks get to take over, and then there's a big bunch of non-interactive tasks, things that are taking more time on the CPU that finish last. We start with a bunch of this round-robin-like outputs, but then we switch to the state of we kind of have some kind of ordering of the tasks that we're implementing here. All right, so I hope that this was a less shitty description of the assignment. It might be overwhelming, and I agree, it is overwhelming, but they all collectively came to tell me, not all of them, obviously not all of them came to tell me this later, but many of them came to tell me later, like they were terrified of this at the beginning, and then by the time they got to the end, it was like, this was way easier than doing the file system stuff. So yeah, if that gives you a little bit of context, then I hope that helps. So at this point, what you should be able to do is use condition variables in a program. I'll push these changes that I've made to the repository up to GitLab after class today. And then tomorrow what we're going to do is start to take a look at these scheduling policies. And the plan is to use some pen and paper basically and start mechanically applying these scheduling policies so that we can see how they behave. And then next week, what we're going to do is spend time with virtual memory fully. That's going to be our topic for next week, is all the virtual memory stuff. I hope that you have a great rest of your day.